you so much for taking out time for this session. We'll get started. From self driving cars to intelligent personal assistants, our world is increasingly powered by artificial intelligence. But what if our AI could think more like us? Welcome to the dawn of neuromorphic computing, a paradigm shift inspired by human brain. Welcome to this session, which we title it as Seeing the World Through New Lenses, Neuromorphic Computing for Real-Time AR Perception. Inspired by the intricate works of human brain, neuromorphic computing represents a bold leap forward in technology. Today, we will uncover how this innovative approach is poised to revolutionize everything from AI to everyday electronics. Imagine you are lost in a giant maze trying to find your way out. You bump into walls, follow paths that lead nowhere, and get increasingly frustrated. That's the kind of how traditional computers work when solving complex problems. They try every single route until they find the right one, which can take a long time and use a lot of energy. But what if you had a brain like a mage master? That's the idea behind neuromorphic computing. Instead of rigidly following instructions, neuromorphic computers are inspired by the human brain. They use artificial neurons and connections that mimic how our brains learn and process information. Think of like think of it like this: as you explore the maze, you learn which paths are dead, which leads to dead end, and which ones lead forward. Your brain strengthens the connection between neurons that helped you to make progress. Neuromorphic computers work similarly, constantly adapting and learning as they process information. This allowed them to potentially solve certain problems much faster and more efficiently than traditional computers. So, what is neuromorphic computing? Neuromorphic computing is a method of computer engineering in which elements of a computer are modeled after systems in the human brain and nervous systems. The term refers to the design of both hardware and software computing elements. Neuromorphic computing is sometimes referred to as neuromorphic engineering. Neuroscientists consider neurons the fundamental units of brain. Neurons use chemical and electronic impulses to send information between different regions of the brain and the rest of the nervous system. Neurons use synapses to connect to one another. Neurons and synapses are far more versatile, adaptable, and energy efficient information processors than traditional computer systems. So, your neuromorphic engineers draw from several disciplines, including computer science, biology, mathematics, electronic engineering, and physics, to create bio inspired computer systems and hardware. Of the brain's biological structures, neuromorphic architectures are most often modeled after neurons and synapses. Neuromorphic computing is an emerging field of science. Various groups have research underway, including universities, the US military, and technology companies such as Intel Labs and IBM. The effort to produce artificial general intelligence, or what we call as AGI in short, also is driving neuromorphic research. Artificial General Intelligence, or AGI, refers to an AI computer that understands and learns like a human. By replicating the human brain and nervous systems, AGI could produce um, artificial brain with same powers of cognition as a biological one. Such a brain could provide insights into cognition and answer questions about consciousness. The high performance computing architecture and the functionality used in neuromorphic computers is different from the standard computer hardware of most modern computers, which are also known as von Neumann computers. Von Neumann computers have the following characteristics. One, von Neumann computers have separate central processing units for processing data and memory units for storing data. Von Neumann computers encode data using binary values. To compute data must be moved between the separate processing and memory locations. This approach is known as the von Neumann bottleneck. It limits a computer's speed and increases its energy consumption. Neural network and machine learning software run on von Neumann hardware typically must provide either fast computation or low energy consumption, achieving one of the expense of the other, achieving one at the expense of the other. Whereas our neuromorphic computers have the following characteristics: collated processing and memory, the brain inspired neuromorphic computer The brain-inspired neuromorphic computer chips process and store data together on each individual neuron instead of having separate areas for each. By collecting, processing, and um, memory, neural net processors and other neuromorphic processors avoid the von Neumann bottleneck and can have both high performance and low energy consumption at the same time. Massively parallel. Neuromorphic chips such as Intel's Lab Lohi 2 can have up to 1 million neurons. Each neuron operates on different functions simultaneously. In theory, this lets neuromorphic computers perform as many functions as one time as there are neurons. This type of parallel functioning mimics stochastic noise, which is seemingly random firings of neurons in the brain. Neuromorphic computers are designed to process this stochastic noise better than traditional computers. Inherently scalable. Neuromorphic computers do not have traditional roadblocks to scalability. To learn larger networks, users add more neuromorphic chips, which increases the number of active neurons. Event-driven computation. Individual neurons and synapses compute in response to spikes from other neurons. This means only the small portion of neurons actually process spikes are using energy. The rest of the computer remains idle. This makes for extremely efficient use of power, high in adaptability and plasticity. Like humans, neuromorphic computers are designed to be flexible to changing stimuli from the outside world. In the spiking neural network, or SNN in short, architecture, each synapse is assigned a voltage output and adjusts this output based on its task. SNNs are designed to evolve different connections in response to potential synaptic delays and a neuron's voltage threshold. With increased plasticity, researchers hope neuromorphic computers will learn, solve novel problems, and adapt to this environment quickly. Fault tolerance. Neuromorphic computers are highly fault tolerant. Like the human brain, information is held in multiple places, meaning the failure of one component does not prevent the computer from functioning. Let's look at some of the use cases for neuromorphic computing. Neuromorphic computing is a highly funded field. Experts predict neuromorphic computers will be used to run AI algorithms at the edge instead of the cloud because of the smaller size and low power consumption. Much like a human AI infrastructure running on neuromorphic hardware would be capable of adapting to its environment. Remembering what's necessary and accessing external sources like the cloud for more information when necessary. Other potential applications of this technology include like our driverless cars, drones, robots, smart home devices, natural language, speech and image processing, data analytics, and process optimization. Neuromorphic computing research tends to take either a computational approach focusing on improved efficiency and processing, or um, a neuroscience approach as a means of learning about the human brain. Both approaches generate knowledge that is required to advance AI. Neuromorphic computing, inspired by the architecture and functionality of the human brain, is poised to revolutionize real time augmented reality perception. This approach uses specialized hardware and software to mimic neural network structure and operation, providing significant advantage in terms of speed, energy efficiency, and real time processing capabilities. So key concepts in neuromorphic computing for AR perception includes your neuromorphic hardware. So you have silicon neurons, neuromorphic chips such as IBM's True North and Intel's Loihi consist of silicon neurons that emulate biological neuron spiking behavior. These chips process information in parallel, similar to the brain, enabling rapid and efficient data handling. Silicon neurons are the fundamental building blocks of neuromorphic computing, which aims to emulate the brain's neural architecture and functionality using electronic circuits. These artificial neurons mimic the behavior of biological neurons, enabling efficient and parallel processing, low power consumption, and event driven computation. Your neuromorphic systems using silicon neurons are high energy efficient, making them ideal for battery powered and portable devices. They emulate the brain's low power consumption while performing complex computations. The parallel and the event driven nature of silicon neurons allows for real time data processing, which is essential for applications such as robotics, autonomous vehicles, and real time augmented reality. Neuromorphic hardware can scale to large network of silicon neurons, enabling the development of complex and capable systems that can handle extensive and varied data inputs. Because of these advantages, these concepts find application in augmented reality. In AR, silicon neurons can process sensory data in real time, allowing for immediate and context aware augmentation of the user's environment. This enhances the AR experience by making it more responsive and interactive. Robotics. Neuromorphic computing enables robotics to process sensory inputs and make decisions quickly and efficiently. This capability is crucial for tasks requiring real-time responses such as autonomous navigation and object recognition. Talking about healthcare industry, neuromorphic systems can be used in medical devices for monitoring and diagnosing health conditions in real time. Their energy efficiency and processed speed make them suitable for wearable health monitors and implantable devices. Talking about event driven processing is a computational paradigm inspired by the way biological neurons process information. Unlike traditional computing systems that operate on a clock driven basis, event driven systems process information only when significant events occur. This approach is central to neuromorphic computing, where it provides several advantages, including increased efficiency, reduced power consumption, and enhanced real-time processing capabilities. So talking about key concept of event-driven processing, you have spike-based communication. Spiking neural network, or SNN, is neuromorphic systems. Neurons communicate via discrete spikes or action potential. These spikes are binary events which either occur or doesn't occur, which can efficiently encode information in the timing of the spikes. Asynchronous processing, since neurons only spike when they reach a certain threshold of stimulation, processing is inherently asynchronous, which means that Neurons operate independently and only communicate when necessary, leading to significant energy savings and reduced latency. Talking about the real-time processing, you have latency reduction. Neuromorphic systems can significantly reduce latency due to their parallel processing nature and event-driven architecture. This is crucial for AR applications where timely responses are essential for a seamless user experience. Energy efficiency. By mimicking the brain efficient processing, neuromorphic computing can handle complex tasks with lower power consumption, making it suitable for portable and wearable AR devices. Integration with augmented reality, sensor data fusion. AR systems rely on various sensors like cameras, accelerometers, gyroscope to understand the environment. So neuromorphic computing can integrate and process this multimodal sensor data in real time, providing and improving the accuracy and responsiveness of augmented applications. Dynamic adaptation. Neuromorphic systems can adapt to changes in the environment dynamically, making AR experience more responsive and realistic. This includes real-time adjustment to lighting, object communication, and spatial mapping. Enhanced object recognition. Neuromorphic computing can improve augmented reality application ability to recognize and track objects in real time. Even in dynamic and cluttered environments, this is achieved through efficient pattern recognition and continuous learning capabilities inherent in neuromorphic systems, and which leads to your improved user interaction. So by providing low latency processing, neuromorphic computing enhances the responsiveness of augmented reality interfaces. This allows for more natural and intuitive interactions such as gesture recognition and real-time feedback, crucial for immersive AR experiences. Scalability and portability. The energy efficient nature of neuromorphic computing makes it ideal for portable AR devices such as smart glasses and mobile AR applications. This enables more widespread adoption and use of AR technology in various fields like healthcare, education, and entertainment. Let's understand more about neuromorphic computing with some examples. So in example one, we'll talk about real-time anomaly detection in sensor data. So imagine a network of sensors monitoring a complex industrial system. Could be a power plant, factory production line. Now, traditional computers analyze sensors data to detect anomalies that might indicate equipment malfunctioning or safety risk. Neuromorphic processors can be trained to historically sensor data to learn the normal patterns of the system. They can then continuously analyze real-time sensor data stream, identifying deviations from the expected pattern in a low power efficient manner. This enables faster and more accurate anomaly detection, potentially preventing costly equipment failures or accidents. Traditional methods for anomaly detection in sensor data often rely on complex algorithms and powerful computing resources. However, with the increasing volume and the velocity of sensor data, these methods can become inefficient, especially for real-time applications. Neuromorphic computing offers a promising alternative for addressing this challenge. So your neuromorphic computing can be used for real-time anomaly detection in sensor data by mimicking the brain. Neuromorphic chips use artificial neurons and synapses to process information in a similar way. Low power consumption. Neuromorphic chips are designed to be energy efficient, unlike traditional CPUs or GPUs. This is crucial for resource-constrained devices like sensor nodes that often have limited battery power. Parallel processing. Neuromorphic chips can perform computations in parallel, similar to how brain processes information. This allows for faster processing of large amounts of sensor data in real time. Machine learning on chip. So neuromorphic chips can be trained directly on the device, eliminating the need to send data to a central server for processing. This is particularly beneficial for real-time applications where latency is a critical factor. Let's look at the approach. Let's break down the approach into 4 parts. So you have you have sensor data acquisition. Sensors collect data, temperature, pressure, etc. continuously, and then you pre-process. So raw data might undergo filtering or scaling for compatibility with the neuromorphic systems. Then feature extraction. Relevant features are extracted from the pre-processed data using algorithms or pre-trained models. Anomaly detection on neuromorphic chip. These features are fed into neuromorphic chip where a trained model identifies deviations from normal patterns in real time. Finally, alerting or responses. If an anomaly is detected, the system can trigger an alert or initiate a pre-programmed response. So benefits of using neuromorphic in this case includes your low power operation, real-time processing, and improved accuracy. Let's look at another example. One of the critical challenges for autonomous vehicles, AVs, is real-time object recognition in their surroundings. Traditional methods rely on powerful processors in the vehicle, but these can be bulky, energy-consuming, and create latency issues. The neuromorphic computing offers a potential solution or faster, more efficient object recognition at the edge, directly on the vehicle itself. Here is how neuromorphic computation tackles object recognition in AVs, mimicking the brain. Neuromorphic chips are built to emulate the brain structure and functions. They utilize artificial neurons and synapses to process information efficiently. Low power consumption. Unlike traditional GPUs and CPUs, neuromorphic chips are designed to be energy efficient. This is crucial for AVs where battery life and power consumption are critical factors. Fast parallel processing. Neuromorphic systems can process information in parallel, similar to the brain. This enables faster object recognition from camera data streams captured by the AV. On-chip learning. Neuromorphic chips can be trained directly on the vehicle, eliminating the need to send data to a central server for processing. This reduces latency and allows for real-time object recognition. So here is the breakdown of the approach in this case. So you have camera data acquisition. Cameras mounted on the AV capture the real-time video data of the surrounding environment. Then you have pre-processing where the raw video data might undergo pre-processing like resizing or color conversion for compatibility with the neuromorphic chip. Feature extraction. Key features are extracted from the pre-processed data using algorithms or pre-trained models. These features could be edges, shapes, or textures that help identify objects. Then you have object recognition on neuromorphic chip. These features are fed into neuromorphic chip where a trained model classifies the object in real time, like car, pedestrian, traffic light. And finally, decision making and control. Based on the recognized objects and their positions, the AV's control system make decisions on navigation, braking, and other maneuvers. So the benefits of using neuromorphic computing for AVs includes real-time object recognition, enables immediate recognition or immediate reaction to identify the objects, improving safety and responsiveness. Then you have reduced latency. On-chip processing eliminates the need for data transfer to a central server, minimizing delays and decision making. Low power consumption keeps battery life increased, or you saves the battery life and contributes to a more sustainable AV design. Improved privacy. Data processing happens entirely on the vehicle, potentially addressing privacy concerns. These are just two examples, and the potential application for neuromorphic computing are vast. As the technology matures, we can expect to see its use expanded in areas like healthcare, in finance, and many other areas. Now let's look at some examples of computational approach that we are seeing in the industry. So we have Intel Labs Loihi 2, which has 2 million synapses and over 1 million neurons per chip. They are optimized for SNN. You have Intel Labs Pohiki Beach computer features, which has like 8.3 million neurons. It delivers 1,000 times better performance and 10,000 times more efficiency than comparable GPUs. IBM's True North chip has over 1 million neurons and over 256 million synapses. It is 10,000 times more efficient than conventional microprocessors and uses power when necessary. So New RRM is a neuromorphic chip designed to let AI systems run disconnected from the cloud. The examples of neuroscience approach, the Tianjin chip developed by Chinese scientists is used to power a self-driving bike capable of following a person, navigating obstacles, and responding to voice commands. It has 40,000 neurons, 10 million synapses, and performs 160 times better and 120,000 times more efficient than a comparable GPU. We have Human Brain Project, HBP in short. So HBP is a research project created by neuroscientist Henry Markram with funding from European Union that is attempting to create a human brain. It uses two neuromorphic supercomputers, SpineCur and Brain Skills, collaboratively designed by various universities. More than 140 universities across Europe are working on the project. So you have Brain Skills, which was created by Heidelberg University in collaboration with other universities. It uses neuromorphic hybrid system that combine biological experimentation with computational analysis and study brain information processing. So neuromorphic computation and artificial general intelligence are what we refer to as AGI. So AGI refers to AI that exhibits intelligence equal to that of humans. Reaching AGI is the goal of AI research. Though machines have not and have never reached a human level of intelligence, neuromorphic computing offers the potential for progress towards that goal. For example, Human Brain Project is an AGI project that uses the spine curve and the brain scales neuromorphic supercomputers to perform sufficient neurobiological functioning, attempting to produce consciousness. So some of the criteria for determining whether a machine has achieved AGI is whether the machine has the following capabilities: reason and make judgments under uncertainty, plan, learn, showcase natural language understanding, display knowledge including common sense knowledge, and integrate these skills in the pursuit of a common goal. Sometimes the capability or the capacity for imagination, subjective experience, and self-awareness are included. Other proposed methods of confirming AGI include the Turing test, which states that a machine is sentient if an observer cannot tell it apart from a human. The Robert College student test is another test in which a machine enrolls in the classes and obtains a degree like a human student. So before we leave, I want to talk about some challenges in neuromorphic computing. Many experts believe neuromorphic computing has the potential for revolutionizing the algorithmic power, efficiency, and capabilities of AI, as well as reveal insights into cognition. However, neuromorphic computing is still in early stages of development and it faces several challenges like accuracy, limited software and algorithms, your inaccessibility to the right software and hardware. Neuromorphic computers are more energy efficient than deep learning and machine learning neural hardware and edge graphics processing unit or GPUs. However, they have still not proven themselves to be conclusively more accurate than our machine learning or deep learning. So combined with high cost and complexity of the technology, the accuracy issue leads many to prefer traditional software at the moment. Limited software and algorithms. So neuromorphic computing software has not caught up with the hardware. Most neuromorphic research is still conducted with standard deep learning software and algorithms developed for van Neumann hardware. This limits research results to standard approaches, which neuromorphic computing is trying to evolve beyond. These are some of the challenges, but no doubt this is going to be a big thing in future. So if you want to focus on new technology, you might want to read and research about the neuromorphic computing even further. With that, we end this presentation, and I thank you for your time today.